Welcome to the Explainer. Okay, let's just admit it. We're all kind of drowning in data these days, right? Files are getting so big that no single computer can possibly handle them. So today, we're going to build the digital fortress that tames all this chaos, the Hadoop Distributed File System, or as you'll hear it called, HDFS.
So here's the plan. We're going to start with what seems like a totally impossible problem. Then we'll build the solution, piece by piece, make it practically indestructible, and then, the best part, we'll show you exactly how you can talk to all that data you've just stored.
All right, so where do you even start with a problem this massive? Well, let's begin with the one fundamental challenge that literally brought traditional computing to its knees. And no, this isn't some tricky riddle. This is the very problem that forced a revolution in how we think about data storage. It's what gave birth to the entire Hadoop ecosystem.
So what's the answer? A really brilliant piece of software that was built specifically for this challenge, the Hadoop Distributed File System, HDFS.
You see, the core idea here is actually pretty simple, but it's also completely revolutionary. Instead of trying to find some mythical giant hard drive, HDFS just says, hey, let's link together a whole bunch of normal computers and just spread the file across all of them. And this is the key concept. It's all about divide and conquer. Your massive multi-terabyte file, it's not one single thing anymore. Nope. It's now just a collection of much smaller, much more manageable pieces.
Think of it like a giant box of Legos. Each block is a standard, 128 megabyte piece. And that uniformity makes it super simple for the system to figure out how many pieces a file needs and where to put them. So a huge petabyte scale file, it just becomes a massive collection of these identical little building blocks. Okay, so you've got your files shattered into thousands of pieces, scattered across hundreds of machines. How in the world does the system keep track of all that? Well, it all comes down to assigning two very distinct roles.
Now, this is where it gets really clever, with this clear division of labor. The NameNode, it's like the head librarian. It doesn't hold any of the books itself, but it has the master card catalog that knows exactly where every single data block lives. And the DataNodes, well, they're the bookshelves, the things that hold all the actual data. This design is so important because it makes the whole system way easier to manage. You have one single source of truth for where everything is.
So we've solved one huge problem, but in the process, we've kind of created another one, and this one could be catastrophic.
I mean, if a few crucial blocks of our file were sitting on that one machine, is our entire file now just corrupted, gone forever? You know, HDFS is built on a really simple, pragmatic principle. Hardware fails. It's not a question of if, it's a question of when. So protection against that failure is baked right in from the start. So what's the secret? It's simple: redundancy. By default, for every single block of data, HDFS creates 3 identical copies and stores them on different machines. All of a sudden, losing one computer isn't a disaster. It's just a Tuesday. But wait, it gets even smarter. HDFS actually understands the physical layout of the computers in the data center, the server racks. And it uses that knowledge to make the system even more resilient. This is just a brilliant design for fault tolerance. Okay, look, the first copy is local. That's for speed. The second copy goes to a totally different rack. That protects you if the whole rack loses power. And the third copy, it goes on a different machine in that second rack, which protects you from a single machine failure over there. It's the ultimate belt and suspenders approach to keeping your data safe.
All right, our data fortress is built, it's spread out, and it's pretty much indestructible. So now what? How do we actually open the gates and bring our data inside?
Well, it really comes down to using the right tool for the job. Let's say you've got this huge organized database of your company's sales history from the last 10 years, and it's all sitting in a normal database. That's a job for Sqoop. It's perfect for those big one-time bulk transfers. But what if you need to capture a constant fire hose of live data, like website clicks or a social media feed as it's happening? That's where Flume is the absolute hero. Think of Flume as a super reliable conveyor belt for your data. The source is where the data hops on. The channel, that's a really critical buffer zone, just to make sure nothing gets lost if there's a traffic jam. And the sink is where the data gets dropped off, safe and sound, right inside our HDFS fortress. It's simple, it's effective, and it's built for that constant flow of data. Okay, our data is in, but now we have to organize it. And how we choose to do that is a really critical decision.
I mean, the right format can be the difference between lightning-fast analysis and a system that just grinds to a halt.
And this is a total game changer. Formats like Parquet and ORC are columnar, which is really just a fancy way of saying they're built for speed. Imagine your data is a huge book. A traditional format like Avro makes you read the entire book from page 1 to the end. But a columnar format? It's like having a perfect index. If you only care about 2 columns out of 100, you can go straight to that part of the index and read only what you need, which makes your queries unbelievably fast. And on top of that, we can also compress the data to save space. But here, you face a classic trade-off. Think of it like zipping files on your computer. gzip is like making the smallest possible zip file for long-term storage. It saves the most space, but it takes a while to open. Snappy is for files you need to access all the time. It's super fast to compress and decompress, even if the file ends up being just a little bigger. So the fortress is built, it's reinforced, and it is filled with neatly organized data. Now for the final and probably the most important step, how do we actually use it? So how do we get in there and talk to our data? Well, there are a few ways, from writing code with Java APIs to using a simple web page. But for raw power and direct control, the go-to choice is almost always the command line interface, or CLI.
And here's the best part. If you've ever used a terminal on a Mac or a Linux machine, this is going to feel just like coming home. The commands for listing files, making directories, moving data back and forth, they're all designed to be familiar, making the huge task of managing petabytes of data feel surprisingly simple. And that really is the whole point of this entire ecosystem. It's not about just collecting data for the sake of it. It's about building a platform that's tough, accessible, and ready to unlock the incredible insights that are hidden inside. The fortress is built, the data is in. Now, what questions will you ask? Thanks for watching.